Okay, so this is what we did yesterday. We did these first three slides, and this is just a reminder that the first law of inertia says that an object maintains its state of motion unless it's acted upon by an outside force. And by saying that it maintains its state of motion, we're saying it maintains its velocity. If it's stopped, it will stay stopped. If it's moving, it'll keep moving at the same speed in a straight line unless some force, some outside force pushes, pulls on it, does something like that. Now, anytime that an object has a change in velocity, we call that acceleration. So basically what we're saying, what the first law of inertia says, it says that if there is a net force acting on the object, if there's an unbalanced force, sometimes we call it, then that will cause an acceleration. It will cause a change in velocity. And so basically that leads us in to the second law, which just very broadly, yesterday we said that the second law states that if there's a net force applied to an object, it will produce an acceleration. Okay? So if the overall force acting on the object isn't zero, so if the net force is something other than zero, it will cause the object to accelerate. And that's a direct result of Newton's first law. And then we just talked very briefly about what net force was. And remember, net force is the vector sum. So it's the one force that replaces all of the other forces. We also call that the resultant force, net force, it's all the same thing. And, we said for this one, because we have 42 newtons pulling this way, if we add those two up, we have 10 newtons pulling the other way, the net force here would have been 32. We said here, for the skydiver, he's got 800 newtons of air resistance pushing him up, 800 newtons of air resistance pulling him, 800 newtons for his weight pulling him down, so the net force would be zero. And in this case, a net force of zero just means he's not accelerating. It doesn't mean he stops. So he's just accelerating. Sorry guys. A net force of zero means that he's moving at the same speed, that he's not accelerating. So he's moving at a constant velocity. So here he's moving at a constant velocity. In this case, on the left, this object is accelerating. So it's picking up speed, picking up more speed, picking up more speed. So this is what we covered yesterday. And now we're going to get to Newton's second law. So we're going to state it out very explicitly what Newton's second law says. So the first thing that Newton's law says is that the force applied to the object, and we should say the net force. I'll add that in right now. Okay, so the net force applied to the object is directly proportional to the acceleration. So those are math words. Give you a second to write that down if you want. And so this is what this means. And this should make sense to everyone. The bigger the force, the bigger the net force is, the bigger the acceleration will be. The smaller the net force, the smaller the acceleration. Now, these kinds of words, these kind of relationships, this is the type of stuff you need to know when you take the SAT or the ACT. There will always be questions about, what does the graph look like if things are directly proportional? So if I were to graph force and acceleration, can anyone tell me what this line would look like? Would it point up, to the right? Would it point down? Would it be curved? Yep, it points up, and it points up in a straight line. So if I could draw a straight line, it would look like this. So when we look at this, if the force is small, the acceleration is small. If the force is big, the acceleration is big. So anytime you see on one of those standardized tests, if you see a graph that looks like this, that means it's directly proportional. All right. Um, and this is why uh, a lot of athletes, work out, get stronger, because if they can apply more force, they can accelerate at a higher rate. Less force, they accelerate at a lower rate. So if you want to be fast, you need to build up your muscles so you can apply a bigger force. If you want to crush a baseball, right, you have to build up your muscles so you can apply a really big force to that baseball. And like if you're in your car and for some reason you want to accelerate really fast, you push down the pedal really hard, that the motor provides a bigger force, bigger acceleration. So does that make sense to everybody? I hope. Okay, good. Now the second part to Newton's second law has to deal with mass. All right. So the more massive something is, the bigger something is, the harder it is to get it moving, right? Because mass equals inertia. We said that before. So the more mass an object has, the harder it is to change its velocity. So the mass of the object is inversely proportional to the acceleration. Now, if I were to draw that graph, it would look like this. Inversely proportional means that I would have the mass here, I would have the acceleration here. Okay? If I have a big mass, I would have a little acceleration. If I have a little mass, I would have a big acceleration. So the graph points down. So anytime you see this inversely proportional, the graph will point down. So that if m is big, a will be small. If a is big, m will be small. Now, I'm going to point out too that for this relationship to be true, force and acceleration, we're keeping the mass constant here. So for here, the mass is constant. So what I'm saying is, let's say that I have a shot put that I want to throw. I want to accelerate it out of my hand, with as big of an acceleration as possible, right? I'm throwing the same shot put. If I apply a bigger force, the shot put has a bigger acceleration. Smaller force, smaller acceleration. Now down here, I'm assuming the force is constant. So I have the muscles that I have, right? And I have the choice between throwing a shot put and a baseball. And maybe a tennis ball. Now out of those three, the tennis ball, you guys know, is the lightest. Baseball is in the middle. Shot put is the most massive. So if I have my massive shot put and I'm pushing it with my muscles, it'll have a small acceleration. Now I have the same muscles, same force. So with the baseball, because it's kind of medium on here, it'll have a bigger acceleration. Now once again, I have the same muscles, but if I have the tennis ball and it has a small mass, the acceleration will be a lot higher. So you can accelerate a tennis ball at a lot higher rate than you can accelerate a shot put. Shot put has more mass, tennis ball has less. This should make sense to you guys too, because you see this in everyday life, right? We used the example the other day. You're at a red light. Do you want to be, you're kind of in a hurry to get to work. Maybe you're a little late. Do you want to be behind a motorcycle at that red light or a semi-truck? And almost every single one of you said, I want to be behind the motorcycle, right? Because the motorcycle has a smaller mass. So when the force is applied to it, it's down here. So when it has a smaller mass, when the force is applied to it, it has a bigger acceleration. It gains speed at a much faster rate. The semi-truck, its mass is really big. So when the force is applied to it, its acceleration is really small. It gains speed at a much lower rate. So you kind of get stuck behind it. If you're not patient, you can get aggravated. So this is what Newton's second law is saying. Big force, big acceleration. Big mass, small acceleration. So does this make sense so far? Any questions? No questions so far. All right. So I got a thumbs up. Nice. So then this is Newton's second law in words, in word form. But we could write this as an equation. So let's do that. And actually, well, this summary, I forgot I put the slide on here, you guys. This summary is just exactly what we just said, right? That anytime I have a net force, it's going to produce an acceleration. A net force other than zero. Acceleration is directly proportional to the net force, and it's inversely proportional to the mass. So that's all the stuff that we just covered. And that's on that PDF. So if you need to, you could write that down in your notebook. And just as a reminder, remember is when we're taking tests from our houses, not in school, you can use all of your notes that you write down. So if I were you guys, like I would have this all in a notebook, I would have it ready, so you're not wasting time. Okay, so now let's do this in formula form. So usually when we talk about Newton's second law, if you were to ask a physics teacher, what they would just say is they would say Newton's second law is that net force equals mass times acceleration. And usually, like when we write this on our equation sheet, we'll write it like this. Here, I'm going to try. I have a tablet, but I'm struggling to use it, so let's see if I can do it. So we would write this down as the net. Really? We would write this down as the net force, F net, equals mass times acceleration. I think I was doing better. So F net equals mass times acceleration. So this is, remember this is net force, okay? So the net force equals mass times acceleration. Now, let's talk about units really quick. What are the units for mass that I said we would use? Grams is too little for us. That's what you used in chemistry. You can type it in the chat. You can shout it out. Yeah, so what are the units that we'll use for mass? In chemistry, you guys use grams, but grams is too little for us in physics because that would be the mass of a paperclip. So we use a little bigger unit. Yeah, right. So we're going to use kilograms. And I know that you know most people just call it kilos, right? But remember, kilo, technically it just means 1,000 of something. So the mass we'll use is kilograms or 1,000 grams. And then we know the units for acceleration. That's meters per second or meters per second squared. So if this is kilograms and this is meters per second squared, then the net force, you guys, is just going to be, the units will be kilograms, meters per second squared. Now, I'm sure you've never heard anybody say, hey, I have like a 10 kilogram meter per second squared of force, right? Because we use the English unit still, most of the time, if we're talking about force, what do we measure force in? In English units. So when you're doing a bench press, you say I could bench, blank, like 225 what? It sounded like someone tried to say it. What do we use for the English units for force? Pounds, thank you. So, yeah, we use pounds. Now, in metric, we're not going to use pounds. A kilogram meter per second squared, it's shortened into a Newton. So instead of writing kilogram meter per second squared, we'll write newtons. And we abbreviate that with a capital N. So the capital N, that would be the abbreviation for newtons. And newtons is force. For the metric, it's the metric equivalent of pounds. So on some of your sheets, because we hadn't covered it yet, for equations on net force, it said there's a 10 N force. That meant 10 Newton, and a lot of people were confused because they thought it was 10 north. So I'm sorry about that, but the capital N, that stands for Newton. Now, so I'm going to write this again. So we have equation number 1, and that is that the net force is equal to mass times acceleration. So this is probably the second most famous equation in physics, right? The first is E equals mc squared. But this, you guys, this is a pretty big deal, because it ties in force, mass, and acceleration, right? So if I keep the force constant, if I keep this constant here, you can see if the mass goes up, the acceleration would have to go down to keep the same answer. Hopefully you guys can see that from the equation, all right? If I keep the mass constant, if the force gets bigger, the acceleration will get bigger, because they're on opposite sides of the equation. So this equation shows that force and acceleration are directly proportional, mass and acceleration inversely proportional. And then if I times mass times acceleration, I get the force. Now the other equation that you need to write down is this one. If there's more than one force, right, then we have to take all of the accelerating forces, all of the forces that would make you go faster. We're going to call those the applied forces. So we'll say F applied. And we have to subtract out all of the forces that would make you go slower, or all of the opposing forces. So the net force is always the forces that make you go faster minus the forces that make you go slower. And that is the one force that goes into this equation, F equals ma. So F net, remember, that's always the one force that replaces all of the other forces. The one force, that would be the vector sum of all of the other ones. So make sure that you have these two equations written somewhere. And I would have the units too. So now let's do a problem with these. What would this look like? So I have a student. They have a mass of 100 kilograms. They're sitting on a skateboard, and their friend is pushing them. Now they are accelerating at 2.5 meters per second squared. I want to know, what is the net force? So let's write down everything we're given in this problem. We're given the mass. So the mass of the student is going to be 100. and the acceleration is 2.5 meters per second every second, or they're getting 2.5 meters per second faster every second, 2.5 meters per second squared. And then I want to point something out, you guys, and this is why I really like to do the experiment with you actually sitting on the skateboards that you make. And that is, if I apply this constant force, you will accelerate, right? You'll accelerate at, a certain rate. In this problem, 2.5 meters per second squared. What that means is that as your friend pulls you down the hallway, you get faster and faster and faster and faster. So when we do this experiment for real, and I make people, pull over 20 meters, which is like 20 yards on the football field, basically. By the end of it, if they pick too big of a force, they can't even run that fast. Because you're always getting faster, you're always accelerating. It's kind of cool. And then what we're looking for is we're looking for the net force. So we know the mass, we know the acceleration, the net force is our question mark. Remember, you write that on your test, 4 out of 10 points. And then we'll write down the equation. Force net equals ma. So now we're at 6 out of 10 points. I just plug in the numbers. So that equals 100 times 2.5. Sorry, I left off the units. It's hard to write. And then, so the net force would be 100 times 2.5. Probably don't need to punch that in your calculator, but if you do, it will give you the answer of 250 kilogram meter per second squared, or 250 newtons. And if we did the conversion, that would be roughly 60 pounds of net force. So are we good? Can I move on to the next problem? I want to do 3 with you today. Okay. So here's the next problem. In this one, I'm given the net force. So I have a net force of 200 newtons. So I'll write that down. F net equals 200 newtons. It's applied to an object with a mass of 5 kilograms. So the mass is equal to 5 kilograms. So that would be the equivalent of 11 pounds, an 11-pound object. Maybe it's like a shot put. I don't know exactly what the weights for shot puts are anymore. So I have a force, applied force of 200 newtons, a mass of 5 kilograms. I want to know what is the acceleration. So I write that on my paper. Remember, that's 4 out of 10 points. And then I'll write down the equation I'm going to use. I have F net, I have the mass, and I have the acceleration. So if I plug in F net here, that'll be 200. And I plug in the mass here, that'll be 5 kilograms. Then I'm left with acceleration. So I'm going to have to use some algebra here. Can someone tell me, how do I get rid of that 5? How do I get acceleration by itself? Right now it's being multiplied. Yep. And if I did the opposite, that would be dividing. So I will divide both sides by 5 kilograms. I'll divide that side by 5. And I'll divide this side by 5. When I do that, those are going to cancel. And I end up, you probably don't need to punch this in your calculator, but if you did, you would get the acceleration is 40 meters per second squared. There you go. Now, I want to make a few points in this problem. Let's say that this was a shot put that you were applying this net force to. If I have a shot put and I'm pushing it with my hand, the only time, you guys, it's accelerating is when there's a force acting on it. So when it leaves my hand, if there's no other forces accelerating it, it'll just move at a constant speed. A better example of this would be a hockey puck. So if I have a hockey puck and it's on the ice, stays on the ice, doesn't go in the air, the only time that hockey puck is accelerating or changing speeds is when my stick is on the puck. As soon as the hockey puck leaves my stick and there's no more forces acting on it in that direction, it'll continue moving at a constant speed in a straight line. So in order for you to be accelerating, a force has to be acting on you. And in the case of the hockey puck, the force is only acting on that hockey puck in the direction of motion when the stick is on the puck. And then I also want to point out, so some of your problems, we're going to do one more, but some of your problems that you're going to be doing for practice, you may have to use your old equations. Because you notice that this has acceleration in it. So I may give you a two-step problem where you have to use F equals ma, and then the second step, you have to use your old acceleration and velocity equations. So just giving everyone a heads up, you can't forget your old equations. If you didn't understand that first unit, you need to get help from me. You need to come to the office hours, because we're going to be using that stuff actually right up until the last day. Okay? So here's the last problem. One more problem. I have a box and it's accelerating at 1.5 meters per second per second. I want to know what is the mass of this box. So I'm looking for the mass here. I know the acceleration, so I'll write that down. The acceleration is 1.5 meters per second squared. Okay, I don't know the mass. That's my mystery variable here. And in order to solve for mass given acceleration, I would need to know the net force. Now, there's 3 forces acting on this box. This is actually the problem we did yesterday, and we looked at in the review earlier today. So if I wanted to find the net force that's acting on this box, remember I gave you an equation, right? That said, if I take all of the accelerating forces or the applied forces, and I subtracted all of those from the opposing forces or the decelerating forces, I would end up with the net force. So for here, these will be my accelerating forces. Why? Because they're bigger. So I would say 30 newtons plus 12 newtons. And then I would subtract it from the forces that are trying to make it go slower, which would be 10 newtons. And yesterday, most of you were able, just by looking at this, you were able to tell me that the net force was going to be 32 newtons. So over here, the net force, 32 newtons. And then now I have to do F equals ma. So on your practice problems, There will be two-step problems like this. And most of real physics, you guys, involves doing more than one step. So we'll plug in our numbers here. 32 newtons equals the mass times 1.5 meters per second squared. And then we want to get rid of this 1.5. We'll divide both sides by it. Sorry I didn't write down the units, but they're there. These 1.5s will cancel. And this one, I do need to plug in my calculator. I'm not thinking that quickly today. So 32 divided by 1.5. I got it to be 21.3. And that would be kilograms. So does that make sense to everybody?